So this is chapter 6, and this really starts us getting us into the meat of the course. This actually gets into programming PLCs. In fact, I'll bring up the application, and we'll start looking at some of the features of RS Logic 500. And by the way, most of these things, once you learn RS Logic 500, it'll make it a lot easier to learn other programming languages, other programming applications, like RS Logic 5000, which is the newest version that Allen Bradley puts out, or Rockwell Automation. Allen Bradley is a division of Rockwell Automation. So you probably need to remember that, because I don't think Allen Bradley's even got a website. You have to go to Rockwell Automation, I think. I might be wrong about that. Also, Siemens, its programming application referred to as the TIA portal. You'll find out once you learn how to program one of these guys and learn the rules, then it's very easy. It's one of those, okay, this is how they do that. It's like when you go out and buy a new car. You know the car does the same thing. It's just you got to figure out where things are, how to set your radio stations, how to, where the wipers, where my wife's van. The first time I rode that, I didn't think about it, and it started raining, and I didn't even know how to turn the wipers on. so it took me a little while to figure it out. But that's what we're talking about. So, I learned way back, the first programming application we had was for the Square D PLCs, which are not even there anymore. Then we moved into the Modicons, which are not even available anymore. We played around with GE PEs, which are PLCs, which are not there anymore. But what we've got is that's the language I learned, and now I can adapt real easy because of learning those programming languages. PLCs, when they first came out, had dedicated terminals. They didn't have computers. All the processing power was in the PLC processor itself, and you hooked up what we call a dumb terminal, which was nothing but didn't have anything in it, and you just actually was running a program inside the PLC. Of course, now that we have our really nice computers, we can do what most programmers do, is create the program in a high-level language, and then, of course, send it into the memory, let it compile and send it into the memory of the PLC. So this guy uses a compiler. So what it does is when we tell it to send it to the PLC, it runs through a compiler and converts it over to that machine language we talked about the other class. So the only thing running inside that PLC is machine language. And then when we upload a program, so that's another term we got to learn, because that's opposite of what you're used to. So your PLC's a computer, and your computer's a computer. So when you get it home, when you download stuff, you're bringing it from somewhere into your computer, but that's not in PLCs. That's not the way it works. So download is a term that we use when we send the program from our application, our programming application, into the PLC. Upload is when we bring bring the program out of the PLC, or information, and bring it into our application. So that's backwards from what most of y'all usually know. But we'll actually open up RS Logic 500. In fact, I've got it in the back, and there's a little more to it. I've got mine set up, but we'll look at some of the things that you got to do on every PLC. The first thing you got to do before you can even talk to the thing. So PLC programming, these are the 5 languages available, structured text, and I'm just going to show you an example. Structured text, referred to as ST, function block diagram, which is FBD, a sequential function chart, which is referred to as SFC, instruction list, and ladder diagram, which is LD, by the way. This is the most widely used in the world, and it's definitely the most widely used in the United States. So this is what we teach here. We don't have time To teach all these languages, we'd literally have to have a degree in programming controllers. But each one of them is set up for people coming up through different paths besides through electrical controls. So this is structured text. This is a language that you actually have to know a lot. You have to know instructions. You have to know syntax. Syntax, by the way, is how a language is written. And it's not syntax like the what we pay on our cigarettes and alcohol here in the state of Alabama. It's actually SY. And so it's the correct way of writing in a language. So when you take English composition, basically, not only are you graded on content, you're also graded on syntax. So syntax would be spelling and punctuation. All that would be considered syntax. So it's SYTAX. So this is syntax. SYNTAX. This is the correct way of writing in a language. So you got to know the right syntax. Even some of the rules that we're going to look at deals with syntax, what you can do and what you can't do. And you'll get a lot of times, hopefully, your application will give you a syntax error. But there are some things you can get by with, which is not, it's not legal, but it's legal under very, very, very small situations, and I'll show y'all that. And if it's even legal at all, you won't get a syntax error. So your computer usually, when you compile it, it'll usually give you errors. It gives you syntax errors that you have in your program. It doesn't mean the program's correct. Because if you used output 1 and you meant to use output 2, as long as the rung is in the right syntax, you're not going to get an error. So it doesn't know what you meant to do. It knows what the correct way that's written. So this is a very, very complicated. This is facts. This is a structured text language for actually a microcontroller called Arduino. In fact, this is one of the programs that I actually wrote. But so you got to learn all these commands. You got to know the right syntax. You got to know the punctuation, what they mean. So these double slashes. This means I'm going to put a comment out there, and comments are something that programmers like to use because that way, when they come back in a year, they know what each one of those instructions are in there for. Instead of trying to figure their program out, they let the program tell them. And we'll show you how you can put comments in your program if you want to. We don't require comments. We do require what we call symbols or tags. But comments are in there for you. And I'll show y'all some of the diagrams for the Festo line. This was written in RS Logic 500. And all the information that Siemens provided, that Festo provided on their programs, on their RS Logic 500 programs. This is a function block. This is basically digital. In digital, you're going to learn different symbols, but these are the industry recognized standards, or the ISO signals. So this is for what we call an AND. It's a block. So that means if this input is true, and this input is true, and this input is true, then it'll generate an output. This is a pulse detector. So what you do is you would be able, if you came up through digital, if you understood digital really well, digital electronics, this would be the language for you. This is the one you could understand. This is the one that you could generate a Boolean equation for and see if it would reduce and make it smaller. So this would be an avenue for people that comes up through Pascal or Java or actually true programming, not these coders that you pull things down. This is true computer programming right here. So those people have a path into programmable controllers. Originally, when programmable controllers came out, they were specifically designed to take the place of relay logic. And they knew all the people that would be trying to program these things came up through that technology. So ladder logic is basically, you looked at the diagrams, you're going to see that it's very similar. So it was real easy for electricians to move over to ladder diagrams. But PLCs have been around so long, and there's so many of them out there now, they're all over the place. What they wanted to do is leave a path for these different programmers coming up through different technologies to be able to program the PLC without without a big learning curve. So this is digital. This is called sequential function chart. This basically is flow charting, which is another computer language. Germans love this. So if you're in the AUT 208 class, we'll show y'all some of these. But basically, it's up in steps. In between the steps, it tells what's required to move to the next step, and that's what these lines are right here. So basically, it's real easy to figure out. It's real easy to troubleshoot. The 1100 doesn't support this, but the compact logics that we'll move into in IoT 196 does support this language. But this would be another one for programmers. Flow charting has been around for years. Flow charting, if you knew the program didn't flow in a flow chart, there was no reason to write it. So normally when computers were so hard to program, it took so much time, they would flow chart the program first, and then they would take the flow chart and create the program. If it didn't work in a flow chart, it wouldn't work in the actual program. This one is not used very often. I've never seen this. This is very similar to a language we call assembly language that we looked at a little bit the other day. Very, very similar as far as the text. This is giving you the actual circuit, and this is the output, by the way. And this would be what the code would be. So you can see this is very, very fundamental. I've never seen this used, but it is a language that's available in some PLCs, but I've never known anybody programming it. This is a PLC program written for OS Logic 500. And what we're doing is we've got a push button out here somewhere. And we've assigned it an address. Okay. So this is the address. So this is the syntax, and we'll get into more detail because there's a little more to it. And we're going to learn the syntax for these addresses. So first of all, we'll start off with an I. So if I use an I, that means it's going to be an input. So this is going to be some device that's connected to the PLC. And then we're going to come up and we're going to put a colon. And then we're going to come up and put a slot number. So I'm going to show y'all, we have Logic Pro, and it's built around a rack-mounted modular PLC. In hybrid PLCs, modular PLCs, and fixed PLCs, the CPU does not occupy a slot. It's inside the PLC. So that means the CPU is not assigned a slot number. So that means you have slot 0. 0 is used for your internal. We call it slot 0, but it's not a slot. Slot number 0 is used to address your internal controlled input and output ports. So the 1100 has let's see, it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inputs, and it's got 6 outputs. So if we can look real close, let me bring it up. Let me bring my camera up. They're going to give you the basic address of each one of these. So if this will focus, come on, yeah. So this is N0, 1, 2, 3. Then we skip over this common, 4, 5, 6, 7, 8, and 9. So there's 10 inputs. By the way, these addresses start with 0. So 0 is an address. It is not a weighted number. So right off the bat, you got to understand that 0, it's not. I mean, it's not a number. It's an address. The analogy I use is that, you got a lot of times the kicker on a football team has a 0 on that's their jersey number. It's not. It don't mean they don't exist. It means it don't mean they don't have any weight. It just means it's some way that we can address it when the guy's calling up there and he kicks a field goal. He knows who's assigned number 0. So 0. So if I wanted to address whatever I have connected coming in on this wire right here, so it's going to be one of these switches down here. In fact, it's going to be this switch right here. Then I would assign it this address. And I don't know if y'all can see. I'm going to come over here, and this is what's nice about a PLC. So here's my inputs, and here's my 10 inputs. And when I come over here and close this switch, it tells you that my PLC sees that input go true, which calls an output. These are my 6 outputs, which calls an output, because there's a program in here right now. So I hit that switch, the output turns on. When I hit that switch, the output turns off. So there's a program running in this PLC from the last time we taught this class. So and the problem we have with this is that this was a good idea, but they didn't backlight. They didn't backlight the LCD display, and it makes it hard to see. And this is why most of your PLCs have gone back to LEDs to represent the inputs and outputs. So what I would do is I would come over here. So this is input 1, 0, which says it's a normally closed, but we're going to talk about this, guys. So I would address this. The way we enter the address is I would put input colon, and it's going to be slot number 0, even though it's not technically a slot. And then what we do is we put a slash, and then we put the port that it's connected to. So when I use that address, I'm addressing whatever input is connected to 0. This guy right here. That's the one I'm using. Whatever's connected there. So when it comes true, those contacts are going to change states. Okay. This would be input 1, this 2, 3, and then this is a common 4, 5, 6, 7, 8, and 9. So right now, if we was going to program this, this would be switch. This would be what we connect. Now, this is the way we enter it, but as soon as you hit enter, what it's going to do, it's going to move the bit number, the bit, because the ports are bits, they're single bits, it's going to move the bit number down here to the bottom, and that's just what RS Logic 500 does. So we come down this line. If this one's closed, by the way, and what we'll see is that when we do our diagram, it'll actually show you that the switch is closed. It'll actually turn, I think, green. These are tags, and which are very, very, and we'll show y'all what's neat about a tag. RS Logic 500 doesn't call them tags; they call them symbols. But you better learn that term right now, because when you get into the TIA portal, which we use to program Siemens PLCs, or the older S7, or RS Logic 5000, or Studio 5000, which is actually this version, they're going to call them tags. They're not going to call them symbols. But this was their first shot, and we'll look at that. So if I was going to do this, first of all, I would have to connect my devices, and we'll come back and look at the rules in a second. So this would be the actual ports. And those are diagrams, by the way. As soon as I find it. It's in here somewhere. No, it's not. Let me bring up another PowerPoint. So this would be the input diagram of the inputs on the PLC. So first of all is we have to establish a common. So your whole lab book is basically wrong, and I'll show you that. So what we've done is we're running syncing inputs, and it's DC. So I'm gonna put a DC power supply right here. So this is provided by the EduTrainer. And then I'll come down from here and I'll make a common because we're running syncing inputs, so all our devices have to be sourcing. Then what I'm going to do is I'm going to come over here and I'm going to draw it as a push button. I'm going to treat it like a push button. I would connect my push button right here. And it's calling for a normally open. The guy's got a big problem with this too. We'll have to talk about this. It's calling for a normally closed. So we'll come up here and draw this as a normally closed, but this is going to be wrong. And I've got this hooked up to input 0 on my internal ports. So in my program, I would address that input : 0/0. Now the next thing they show here on our diagram is a normally open. So it connects between my plus common, because we're running syncing inputs, so and we're going to use a normally open push button. And let's see if they give them names. That was it. That's where it should have been. So we'd put the names out here too. So they're calling the name. They're calling them push button, and they're calling it switch 1 and limit switch. So notice the limit switch has a different symbol. So this is hooked up to port 2. So we'd come over here on our diagram and we would have to draw the legal symbol for a limit switch. So I'd come over here and it's on 2. It's normally, what was it? It's normally open. So this is a symbol for a limit switch. And it goes to input 2. They call this push button, and we would write the name up here. I don't remember what it's called, but I'll just put something up here. But we'd go ahead and write the name. Then what we would do, and this is the way we would wire it. So then we get over here to the other side, and we've got 3 outputs. We got output 0, and we got 2 outputs, output 0 and output 1. Well, the way we address those is we use O, and this is going to give us problems too, because an O and a 0 look a lot alike. So when Siemens came out, they changed their outputs to Q. So that's one big difference between Allen Bradley RS Logic 500 and also RS Logic 500 and Siemens. The Allen Bradley 5000, you'd actually select an output and it puts all this information into you, which is pretty neat. So I'd come up here and I'd start off with a letter O. I'd put a colon. Since it's internal, I would say, okay, it's in slot 0. I'd put a slash, and this is the way I would address it in my program. As soon as I hit the enter key, it's going to move down, it's going to move the bit number down there. So we got one called motor and one called light. Since I can't see these at the same time. So I would come over here. So we're running sourcing outputs. So I'd come over here and my DC power supply needs to be hooked like this. And then I would come over here and I'll run a common for my devices, the minus. Okay, so we'd come over here, and over here we would put whatever this was. I think it said motor 1. Yeah, motor. Now normally we don't connect the PLC. What we would do, let's do it the way we would do it. I would have a relay, and I might call it M1, and then over here I'd have what we call a power diagram, and over here this could be 120 volts, and then I would put an M1 contact over here, and then over here would actually be my motor. In fact, we don't draw motors this way. We draw it in a wiring diagram. So we would come down here like this, and then this would be, we'd have two or one contact normally on this, and then our motor would be down here, and this right here could be 120 volts. And then the other thing that they have, the other output that they have, so very seldom do we run motors off the PLC. They have a red pilot light. So we'd come over here, and we'll put the symbol for the actual symbol for a paddle light. So on your inputs and your outputs, you use the electrical symbols, and this is the red pilot light. Okay, and this is the way we would wire our PLC. Now, and what you do over here, with no series circuits, they're all one load, normally one input. If we put multiple inputs, then we have wacky stuff. It would be hard. So even if we had two inputs in series in our line, in our relay diagram, each one of them would be assigned its own input. And the inputs are not in parallel because you have a circuit, you have an electronic circuit, and each one of them are individual. They're not in parallel. To be in parallel, this side and this side would have to be connected together. These are not in parallel. We put them in parallel or whatever inside our diagram. So what we would do now is we would bring up our PLC programming application. Here it is right here. And what we would do is we would come up here and tell it to create a new program. And the first thing you're going to have to do is select what CPU you're programming. So RS Logic 500 can program a lot of different PLCs. So this application is not dedicated to one CPU. It's dedicated to a lot of them. So you need to know this information. Normally, it's written on the right side of the PLC. So this is a 1763-L1 116BWA Series B. But what's nice, that's deep, but it's also called Micrologic 1100 Series B. So that's what we're looking for. So when I go into my program, I'm going to go down through all these. I'm looking for the Micrologic series of PLCs. So there are. And I'm looking for the 1100B. So now what it does, it pulls in all the instructions and everything that's supported by this PLC. So it starts off with rung 0. And rung 0 is going to be the end instruction. So the end instruction is stuck in there automatically. So one thing we've got this. So here's our instruction palette. So here's all the instruction that this PLC can do. Now this is all of the instructions that RS Logic 500 supports. So you see when we go into some of the palettes, so this is the instruction palette, some of them are grayed out. It means RS Logic 500 supports them, but this PLC does not support them. So that's one thing that's really important, that you pick the right PLC, because it's not going to work. It's not going to compile over. When you send it over, it's going to say you got a big problem. So first thing you do, no matter which application I've ever programmed, the first thing you do is select, well, that's not true. Normally, and this is backwards for RSLogic 500, notice I did not give this program a name. So RSLogic 500 is not going to require a name until you download it into the PLC, which is very strange. Or you save it. If you save it to your flash drive, or you save it to your hard drive, or you save it to a network drive on your computer, it will ask you for a name. RSLogic 5000, you enter the name first, and then you select the CPU. The TIA portal, you enter a name for the program first, and then you select the CPU. So it's kind of a little backwards on here. So I'm going to go back to user. So user, this is the palette that you can put the most used instructions that you have, that you use all the time. So instead of going through all these palettes, finding these instructions, if you use one all the time, you can put it into your user palette. And I'll show you how to do that. So the first thing I'm going to do is I'm going to select this, and this means I'm going to insert a rung. So it puts a new rung. Now notice my rung becomes 0, and then the end moves to rung 1. So the first rung in Allen Bradley programs will always be rung 1. It says I've got an error. That's what the E means, and it turned red. Well, what's my error? Well, I have no inputs and I have no outputs. So what I'll do is here's a normally closed. I'm going to pull that down. And notice my rung turned green right there. That means that's where it goes. Now it's got a big question mark up here because I haven't assigned it an address. But what you can do is you can go ahead and develop your program first and then come back and assign addresses. Or you can identify them, or you can also identify them another way right off the bat. So then it says I need a down drop. I'll put a down drop right here. Inside that, I think I need another contact. I think I saw a relay coil here. Let me bring my diagram back up. And then I put an output here. We call them coils, but they're not. They're outputs. And then I need another output down in my down drop. Where's my program? Oh, here it is. Okay. Nope, that's not it. Oh, that's up. All right. It's got the ladder up there. So right there. Okay. So I need a output right here. Okay. Then what we're going to do is we're going to assign addresses. You can assign the addresses as you go by just hitting on the question mark. And I'm going to put N colon 0/0. And then when I hit enter, now it's asking me for a symbol. So this is where I'm going to assign it a name. And we'll show you what we're going to do this. So we're going to require symbols. This is where I would put a comment. This is where I put a description. Instead of using theirs, I'm just going to use my own because I don't want to keep going back to the diagram. I'm going to come up here and I'm going to assign this to input 0/1. Hit enter. I'm going to call this push button 2. Okay. So notice the symbols are in green. I'm going to come up here and assign this input 0/2. Okay, hit enter, and I'm going to call this limit switch. By the way, you can limit switch 1. You can use lowercase. It'll make them uppercase when it goes in there. I'm going to call this motor 1. So need to do the output colon 0/0. We'll call this motor 1. And I'm going to come down here and assign this output colon 0/1. And we'll call this red light. Yeah. Okay. Now, everything is correct, but it still says I've got an error. So that's what this little guy is up here. This verifies the project. So what it's going to do, it's going to select for syntax error. You can do this every time you add something if you want to, but for some reason these errors do not clear. On RSLogic 5000 it does, but here we got to check it. And notice it went away, so it means I've got no syntax error. It doesn't mean it's right. It just means it's written correctly. So out here, if I wanted this to be output 2, but I put it on 1, it's in the right syntax. So that does not mean the program's right. It just means it's written correctly. Okay, so there's my program, guys. And why we use symbols. So let's say I'm going to come out here and I'm going to highlight this, and I'm going to put another rung in there. So as soon as I hit the insert rung, or supposedly, it moves to end, so your first rung will always be 0. It says I've got an error. But what I'm going to do here is I've got one push button out there. Now in relay logic, we can only use that push button. That push button, it's got that one contact 1, but this is not a physical device. This is a program. So what that means, I can come down here, and instead of me knowing the address up here, I'm just going to put PB1. And what did it do? Well, it filled in all the information. It filled in the address for me, which is pretty cool. I can come down here and pull down another contact, and then I can assign this to motor 1 coil over there, or simulated coil. Now, by the way, as soon as you start typing, it's going to bring up these symbols. So I've already found it. I'm just going to click on it. I'm going to hit enter, and it automatically filled in the address information. And that's the power of symbols. Not only does it name each one of these addresses and give you a little idea of what you're dealing with, it also automatically pulls in all the address information for you. And I'll show y'all as we move along how you can set this up before you even write your program. And once you've matched a address to a symbol, you can just use symbols from then on, which makes writing programs so much easier because now you don't have to worry with addresses. So this is like your contact list in your phone. So how many people know the address, phone numbers of everybody in their contact list? You don't. I don't. I had a guy call me and wanting to know my son's son's phone number, and I told him I didn't know it because I didn't. Because why? I bring up my contact list and I say call John, and it calls him. So using symbols is very, very powerful. Other PLC applications calls it, and I can break down other here. We can reuse coils, by the way, but we're not going to do that. That'll cause all types of problems, and we'll talk about when that's legal. So over here, I'm going to have to assign it to another output. So we're not supposed to duplicate these coils. That can cause, the problem is if you duplicate coils, you don't get a syntax error, but your program is not going to work right. And you can download it into the PLC, and it could cause all types of problems. So don't reuse outputs. Output 0/2. And we'll just call it output 2. By the way, these are comments. Comments are just what we will tell what this does. So notice comments appear in yellow. So usually in comments we give more detailed information, something that I can use when I come in here in 2 years and figure out, Rich, why did you do that? Well, if I've got that comment up there, it's going to say exactly why I did that. So this is really, really good documentation. Comments are not required. Symbols are not required. Symbols in this class are required. And why? Because when you get into these bigger applications, these newer applications, they are required. So you might as well get used to doing them now. And comments are not required, but you'll see in most well-written programs, most well written, they use a lot of comments. And what that does is they know they might have to come back in here in a year and figure out why in the heck they did what they did. Well, now it'll come up here and tell them that. We're going to check for syntax errors. I need to put a syntax error in here on purpose. So let's say I come over here and I put another output. Okay. Okay. And then what I'm going to do now is I've got a syntax error. I've got a series circuit in here. And when I come up here and do this, notice all of a sudden I got this new pop-up that pops up on the bottom. And now I can click on file 2 and it says invalid output instruction position. So right off the bat I know I've got an output in a position it's not supposed to be at. So that's what it does when we do that. It checks to see if we've got any syntax errors. Like I don't put a load in a rung. By the way, it'll check your in syntax when you compile it, but it's always good to do this. And then of course I can X this out and close it out. By the way, all your keys work, so I can come up here and highlight this, and then I can hit the delete key on your keyboard, and it'll delete that. And now when I check it, it has no syntax error. It doesn't mean it's right, it just means there's no syntax error. So what we could do now is we can save it, which means this is not downloading it to the PLC. We could save it without downloading it. Okay. But what we're going to do is we're going to come over here, hit on oh gosh dog it. I'm missing a thing that goes right in here. Oh, it's over here. No, it's not. I'm missing one of my. Yeah, this is normally over here. So I'm gonna come over and hit this. I'm gonna hit download. I've already selected the PLC, so I'm gonna show you how we set up communication. So now it's asking me for a name. I think I've already got play in here a couple of times. Okay. So this is one big difference between most of your PLC programming applications now is they ask for a name when you create the program. RS Logic 500 does not ask for a name until you upload it. So that's one big difference. By the way, we'll talk about extensions and let y'all so you can find your projects real easy. This is where it's going to put it at. So if you had a thumb drive and you put it into your computer instead of saving it on the computer where you'll have to come back and delete them later on, you can come up here and you can specify where you want to put it at. By default, it usually puts it in your document file on your on yours. Mine is putting mine on my file server. So G Drive. This is a file server that we're putting that on. So, and by default, usually when you save it, when you select that folder one time, it's going to keep that folder until you change it. So if you wanted to bring in your thumb drive and plug it into the computer and save all your programs on that would be fine too. But don't forget to bring the thumb drive with you when you come to school, because I've got to see all these programs actually operate. So we'll come up here and we'll just hit save. It's going to come up here and it's going to check syntax again. It's asking me, do I want to download the file from this unnamed CPU? We'll tell you how you can actually name that, and I'm going to say yes. Right now, my PLC is in run mode. We cannot download it when it's in run mode. So what we have our PLC set up is for what we call remote, where I can switch it between the modes with the computer instead of doing it at the PLC. So we'll show you this too. So I'm going to say we're going to switch it into offline mode. Now we can upload it. Now do we want to switch it into run mode? So now my PLC is running this program, and it's asking me, do I want to go online? So now I'm in monitor mode. This is another, so it's showing me right now what's going on. So it's showing me this right here is true. So I'm going to come over here and close switch 1, and you see which switch 1 went true. It showed me that this output went true. So I'm going to come over here. This is output 0. I'm going to flip my camera up real quick. So there's output 0. That light comes on. So if I had anything connected to this, it would actually be running right now. So I got switch 1 on, and then my program's running. When I look at my display, if we can see it, I don't think so. Like I said, it's showing me input 1 is true. It's showing me output 2 is true. But, so what's happening is this is actually showing my flow. So if I come up here and close switch 2, here comes switch 2, notice this guy right here closed. Okay. Now, this is not, these are the same ones, so it's telling me that this guy right here, so this will never work, by the way, because when I change the position of this switch, this is going to open. So 2 will never come on. So let me show you what I'm talking about. So I'm going to change the switch. So you can see they're always in opposite state, because this is a examine if open. This is an examine if closed, and we'll talk about that. And we really got to learn that concept. So this is, but it didn't tell me I had a bad rung because it's in the right syntax. So no matter what I do, because of this input right here, these will always be opposite of each other. So when this one's closed, this one's open, right? Right? So, and then when this one's open, this one opens and opens that one up. So here's switch 2. So I'm going to leave switch 2 on, and I'm going to switch switch 1. And output 2 never goes true, because if it went true, it would turn green like that. So this tells me a lot. I mean, this tells me, so I get a flow. I know my programs, it may be okay. I know this rung right here is bad, but I didn't get an error, because when I wrote it in the right syntax. So just because you don't get a syntax error when you check it, it does not mean the program is. So we wrote our first program. I mean, this is, or I wrote it for this PLC. Okay. So this is RS Logic 500. This over here is called the project tree. We'll explain this. Most PLCs have that. This up here is the instruction palette. All of them have that, where we can come in and we can pull instructions into our program. The palettes will be, here's bit, by the way. User, this is where you put the instructions that you use most often. So instead of having to go through all this palette and find this jump instruction, which is way out there, I can put it into my user palette, and now I can use it real fast. So we're going to be using bits, bit instructions. This is our, we're going to be using latch and unlatch. We're going to be using these right here. That's our, we call it a coil, even though technically it is not a coil. It's software, it's a program. But we'll call it a coil. Just because it come up from PLCs. These over here we're not going to use. We'll use them in PLC 2. Here's our timers and counters. We'll be using these. We won't be using this guy right here, but we'll be using timer, on delay timers, off delay timers, count up, count down, and reset. We'll be using those this semester. Here's our we won't be using any of these. You have to advance through the palette right here, by the way. Compare instructions, we'll be using those in ILT 196. Math, add, subtract, multiply, divide, square roots. Negate, we'll have to learn that. Convert from ASCII to data, and from data to ASCII. So this allows us to send ASCII information, which is pretty cool. Inside here, we're going to use this semester. We're going to use the move and the move with mask. I don't know. I know we're using the move. I can't remember if we're using move with mask. Here's our logic instructions that we talked about. File. We won't talk about this. This gets us some pretty heavy stuff, by the way. Sequencers, shifts, we'll get into that. And if you take 196, we'll talk about that. Program control, we won't talk about anything in here this semester. This is our jumps, jump to label, jump subroutines, returns, and that neat stuff. ASCII, we can play with ASCII strings. A string in computers is multiple characters. We won't be dealing with this one in both class. Trig, this PLC doesn't support the trig instructions: sine, cosine, tangent, arcsine, and we'll deal with some of these in PLC 2. So if it's grayed out, it means RS Logic 500 has that instruction available. It's just not supported by the MicroLogic 1100. So any questions? We're going to go back and actually look at the rules now that I followed, but even though I followed the rules, I still had a problem. And my problem was, here I'm using normally open, here I'm using normally closed. When I open up this one, then this relay drops out, which means this opens. So so this output right here never becomes true. But it's in the right syntax. So here's the rules. That my program was a little bit like this. But see how we address the inputs and the outputs? List the rules for creating PLC ladder diagrams. Convert a relay logic diagram to a PLC diagram, which we'll do. Correct. Normally, what they'll do is they'll give you the relay diagram, and then you're going to come up and you're going to create the PLC diagram for that. The diagrams here are until we get into logic, which will, if you take PLC 2, our diagrams are going to get more complex. Usually these are going to be real small programs because we're just trying to teach a concept by going through these instructions. Create a ladder logic diagram on PLC is offline. So to create the program, your computer has to be offline, which means you're not communicating with a PLC. So we'll talk about the modes the computer's got to be in and the modes that the PLC's got to be in to download and do other types of stuff. Use the force instruction to troubleshoot. We don't do that right off the bat, but we will do that, and I'll show you all that. So to create a relay logic diagram, use input devices symbols and output device symbols. Input and output port addresses are assigned on each input device when we write our program. Each circuit is called a rung, of course. Going the wrong way. I know it's almost time for another break, guys. Rule 1. You'll get an error if you do this wrong. Arrow that will not clear until it's corrected. With RS Logic 500, input instructions must be placed between L1, the left vertical rail, and the rungs load, right, which is attached to the right vertical rail. We have no overload contacts in PLCs. So your load is always going to be connected between L2 and the control devices. It should be noted that any instruction that the programming application places on the L1 side of the ladder diagram is considered an input instruction. And we're not going to deal with RS Logic 5000. Rule 2. Output instructions are placed between the rungs control devices and L2. Nothing is allowed between the rungs output devices and L2, which is the right vertical rail. Ignore the RS Logic 5000. I thought I took those out. Rule 3. All input and output instructions are replaced horizontally. We don't have to worry about that. That's automatic. Rule 4. A rung's output instruction must not be placed in series with other output instructions. Multiple rung output instructions can only be placed in parallel in another line. One output instruction per line, one or more output instruction per rung. This is true. The book does not say that. The book is wrong about the way they do that. Rule 5. This is an error that will not clear until you correct it. Program flow is from L1 to L2. Rule 6. Automatic. Rung numbers are automatically placed on the left side of each rung's first line. So y'all saw that happen. So I don't know. Rule 7. User defined, not automatic. Each input or output device instruction address is entered above each instruction symbol. This location is predefined by the Ladder Logic PLC programming application. Note, one logical address for a bit instruction is entered. Once the logical address for a bit instruction is entered at the top of the symbol, the bit address is displayed below the symbol once you hit enter. I need to add this. A block input instruction, which we'll look at later on when we get into counters and timers. A block input or output instruction's logical address is entered in a predefined location inside the device's symbol. So we'll look at that. 7. This is optional. Each input and output instruction should be assigned a symbol name. In new PLC programming application, these are called tags and are required. Once a symbol name has been assigned, the name can be used to repeat an assigned address within the instruction. This is required in this course. It's optional in RS Logic 500. It is required in this course, and they are green. So if you type in something and it comes up against a yellow background, it means that is a comment. So I had that happen several times where people try to use comments for instructions. For symbols. Rule 8, user defined, not automatic. Optional comments should be added to each instruction symbol and rung. Comments are what we put so I can come back in there later and figure out why in the heck I did what I did. Rule 9, user defined. RS Logic's optional symbols should be given a name that relates to the instruction's function in the control circuit. Using symbols allows a logic address to be addressed by name instead of numbers. That sounds like the same rule on it. Rule 10. Input and relay contact instruction address can be used multiple times within a PLC program. Output instruction addresses should only be used once. Now notice I said should, and I'll talk to you later on. There is one situation where we will repeat those addresses, and these two instructions are valid. So that rung is that is not true, and for this reason you will not get a syntax error, but you'll have problems with it. So this is rule 6. Let's see, 7 we looked at, and this is what we showed about. So this is actually a program. This is a program that's. Let's go ahead and pause, guys. Let's take a break. So let's come back. I think we've already talked about this. Comments are optional, automatically placed above the rung of an IO instruction, placed on top of each rung, and it's on a yellow background. And what we use this to describe the function of the rung, or actually the function of the object. So this is a part of the Allen Bradley. So this is actually a rung that comes out, that's from the PLCs that's running the Festo line, and we'll be referencing those. But you can see these comments, they're in yellow. This is a symbol, which other PLCs call a tag. But it says, okay, so it says, this explains this. The F start bit is set if an initial position to the start button, control panel, or the start button to remove control is pressed. The F start flag is reset, and so this person is telling us exactly what's going on. So what that means is now when we got these programs from Festo, we could look at these programs and we could figure out what they do. Now, what we're going to do, if you take PLC 3, which is ILT 212, which you can take after this class, by the way. It doesn't have a prerequisite. The prerequisite it has is this class right here. But what we're going to do is we'll move over to the Siemens PLCs. And we're going to take these programs and we're going to convert them over to the Siemens application. And what you have to understand, different applications are they're different operating systems. So that's the difference like between an iPhone and an Android phone. So you can't run a program written for an Android phone. You cannot run it on an iPhone because they have different operating systems. They have different drivers. Everything's at different addresses, which the operating system has to know. So I could, when I showed y'all that system information part, I could look at the keyboard, where the keyboard on the computer's at, and that's been the same address ever since the IBM personal computer hit the market. The keyboard has been at the same address. Now they've expanded that, but an Apple, when they designed theirs, they probably put the keyboard at a different address. So if the keyboards are different addresses, and then you load in an application that doesn't have drivers in it, it uses the drivers that are inside there, then it has no idea what to do. So comments are very, very important for us when you take PLC 3, because it tells us what the rung is supposed to do, and it gives us a better understanding when we convert it over to the ATIA portal or S7 software. It gives us a little better deal of what the thing's going to do. So if you're a really good programmer and you looked at my program, my Structure Tech program, I always double slashes. I put all those comments out there. So good programmers always comment their program. They always comment their program. And some companies require that. So if you get fired, then another employee can come in there and figure out what you did. We had out of U.S. Steel, we had an engineer called Dan Stiff, and he was smart. And he went into the tin mill and he designed and built some motor drives. He did not document anything for other people. And then Dan retired, and then he decided he would be a consultant. and so any of the people out there at U.S. Steel they let him get by with this. So Dan was making like $100 an hour to come out and fix stuff that he designed, because some bosses should have got fired over that, because they didn't go to check and see if Dan documented all the stuff that he designed. So Dan had it documented, but he kept it. He didn't give it to U.S. Steel. So Dan Stiff, he was a very smart man, made a lot of money. He probably made more money after retired than he worked for U.S. Steel. So very smart man. It is a true story too. So he was an engineer out there and very smart. So this is another one. You can see every rung is commented. They actually put comments above each instruction. This is so you can comment the whole rung, and then you can comment and say, okay, this is this on this rung, and it makes the comments a lot more simpler. We'll look at latch and unlatch. We'll definitely look at those. We won't look at this instruction. This is one of the instructions. This is called a one shot rising, and we will get into that if you take PLCs too. And also, PLC 3, we'll have to learn what it does, but it's only one big instruction that we have to pick up. So if you want to take ILT 212 and get into the Siemens PLCs, then you can take it. You don't have to take ILT 196. You can take it after this class right here. Not covered in the textbook. With RS Logic 500, a symbol is an optional logic text address assigned to an input or an output instruction's physical address. Once a symbol has been assigned, so the physical address is like my phone number, or like your friend's phone number. That's the physical address. That's a bunch of digits, and that's a number. But what we can do is we can assign that number to a name inside a contact list. Well, that name is not the phone number. It's what we call a logical address. So when I go up here and select John, which is my son, my phone will go into my contact list and find that number that's referenced to that. And that's the same thing to do here. So using symbols, in fact, what we can do is just like your contact list. And I'll show you how to do this. We can assign symbols to an address before we even write our program. And then once we do that in a symbol chart, then we can just write our whole program by typing in names instead of typing in numbers. So I'll show you how to do that. Once a symbol has been assigned, the symbol's name can be used instead of the physical address. In newer PLCs, these are called tags, and these are required. So for this reason, we're going to require you to use symbols in this class right here. So this is the way we start up. So the first thing we have to do is figure out how we're going to communicate with our PLC. So what I have is, right now, I was going to use Ethernet IP, but I couldn't get it working. So this PLC gives us two options we can use. So here's my communication cable right here. And then this plugs in the side of the PLC. It's got two ports on here. It's got an RJ45, which is for Ethernet, hardwired Ethernet. Some of y'all don't have that, but if I was at home and I had a router and I had a computer, if I wanted high speed, I would hook up to that port. I wouldn't use Wi-Fi. Wi-Fi is just not there, guys. So this is for Ethernet IP. This is for a interface called DH485, which we'll talk about more. And this is the one I'm using because it's a peer-to-peer, which means peer-to-peer means both computers. It's designed to hook from a computer into the PLC or from a computer to another computer without having 15 or 16 or 300 computers communicating at the same time. And then what I have to do is, this is an RS-232 interface, which is no longer supported. So I've got this dongle right here. So this is RS-232. I'm not going to disconnect it. I'll show y'all to you later. But it's called a DB connector. It's in the shape of a D. And I'll show y'all this when y'all come in next week. So this is no longer supported, and we have a lot of interfaces that's no longer supported, but you can buy a go-between. So this takes standard USB, which is an A connector. I'm sorry, a B connector, standard B connector, and it goes into this dongle that takes USB and converts it all to all the signals that's required for RS-232. And of course, this comes over to a serial port. To my USB port. But this deals with what we talked about before about parity. So this is using so as soon as you install that dongle with plug and play. So I'm gonna go into control panel. Dang, Rich, I didn't want to do that. I'm going to go into control panel. By the way, on Windows 10, control panel is not in your main menu, but you can add it. So this is where you can go in and configure just about it. So a while ago I was having problems with sound. So I came in here to sound. I came in here, clicked on sound. I'm trying to click on sound, guys. So I came in here and clicked on sound, and then I came up here and I selected my output device, and then I set it up for I made sure it was set up for my headset. So if you ever have problems, this is where you would come, and you can switch between the speakers on your computer, headsets, and all kind of neat stuff. But what we're going to do is go down here and go to System. And this is called Device Manager. Device Manager shows all the hardware that's being controlled by my operating system. So all the drivers and everything. So this is going to show us, it's going to show us a lot of information about it. It'll show us resources. It'll show us addresses and all kind of neat stuff. And by the way, in Device Manager, if you're having problems with something and you bring up Device Manager, it'll show up with either an X or a question mark or something over here in the list indicating you've got the wrong driver or whatever, and it'll allow you to reinstall the driver if you've got it. So this is a really good place to go. So this is everything that's controlled by my operating system. So as soon as I hit that dongle in there, it added COM ports when you install the driver. These are ports that use. I'm gonna come up here, and the problem I had, and I'll have to show y'all that, is by default my communication was trying to use port 5, and my USB dongle is actually on port 7. I'll show y'all that too. And when we click on this, it says it's working properly. We can reinstall the driver, or we can make it update the driver, but it's doing okay. But this is my port settings. So this is where we can set if we use parity. So this is parity. So right now we could set it up for even or odd, and or we can set it up to be always a 1 or always a 0. Depends. So right now we're saying we're not using parity. We talked about that when we was in numbering systems. This tells us the number of data bits. So we're sending 8 bits. This is the speed. This is what we call the bit speed. So this is 9600 bits per second. This was configured automatically, by the way, and I'll show you all that. Flow control, we're not using any flow control. That's all those NACs and those not acknowledges and all that kind of stuff that we looked at before. And we're using one stop bit. We're not going to talk about that. That tells we will. That tells the receiver that every time we see a stop bit, it says, okay, we're ready for the next. We're ready for the next byte. So RS-232 or serial communication is pretty interesting. You won't have this in your list unless you have some type of dongle that uses this interface. And when you put it in there, and this one you actually have to install a driver. So when you look at your device manager, odds are you won't have any COM ports. But I had to go here because my PLC was set to look at COM port 5, and what I found out, it was actually on port 7. So as soon as I just did that, everything worked okay. So device manager, very, very important. You don't have to come through there. You can go in your search bar and type in device manager and bring this up. But this shows everything that's being controlled by my operating system, all the drivers in there. So pretty neat. So y'all probably didn't even know it was there. So a lot of times we can go in, like I said, if we need to reinstall a driver, if we get a corrupted driver, we can come in Device Manager and tell it to, if it's available. If not, and it's a major manufacturer, it'll actually automatically go out to the website for that manufacturer if that's defined, and it'll actually get the newest driver for you. So I had to do that because mine wasn't using the right port. So this popped up. So for some reason it switched over to speaker. So I just came up here and hit right clicked on this and just set it as my default device. So that's where if your sound's not right, if your microphone's not right, and then it also gives you the ability to test it, by the way. So what we did, first thing we need to do is figure out how to establish communication with the PLC. So I'll show y'all this, which is one way, and then we can also use Ethernet, what we call Ethernet IP, which is an industrial protocol. So IP stands for industrial protocol. On the one we use for the internet, it's called TCP/IP. It stands for Internet Protocol. So that's how we put the package together. Start a new program. I showed y'all how to do that. Select the model of the PLC. You need to figure that out before you start the new program. By the way, if you know the model of the PLC does not have to be connected to the computer to write these programs. So you can write the program at home. All you got to do is just make sure you select the CPU so it'll bring in the right instructions for that CPU into your program. And what we do, we call it offline programming. So your application's offline, and then you can come in and connect it up. So you can have all these programs stored somewhere, and you can modify the programs while your line is running, and then go out and keep the old program and go down and download the new program when you're ready. Check it out. If everything's okay, then you're okay. Configure your I/O. We need to talk about this. We'll look at that later on, and then you start programming. After constructing the relay logic, assign addresses to each of the output devices. Note that this is usually done during the construction process. Connect the input-output devices to the PLC port. We usually do that before we even start, and we create the PLC ladder diagram. So I've wired the CPU for you, and in PLC 2, we'll let you wire that PLC up to this edge trainer, and you'll have to wire the PLC if you take the PLC 2 class. You'll wire the PLC. So programming off, we got two. The programming application has got two modes. It's got offline, which is we have to put it offline when we create a program, and then online when you're going to download it into the PLC. So that's the only two modes that your application can be in. Your PLC can be in three modes. It could be in the run mode. In the run mode, if you switch it to the run mode with a switch, and I'm going to show you how to do that on 1100, so you can switch it in the run mode, then you can't download a program into the PLC when it's in the run mode. And then we have the program mode. This is where we can download a program into the PLC. Normally we'll have a switch on the PLC. On the 1100 we do it through the front panel, where you can switch it between these two modes. So program mode is when you download a program into the PLC. Run mode is when the PLC will start running the program automatically. As soon as you switch it into run mode, it'll hit rung 0 and it'll go start from there, and then it just loops. Most of your new PLCs have what we call a remote mode, and that's what mine is in, a remote mode. In the remote mode, you can switch it between the run mode and the program mode with your computer. It does it automatically. You saw it where it says it's in the run mode. Do you want to switch it? And I said yes. And then it says, okay, do you want to switch it back to the run mode? And I said yes. And then it says, okay, do you want to go online so you can see what the program's doing? And I said yes. So normally in this class, we will put it in the run mode. A lot of PLCs, to switch it between the three modes, they use a key. And what they can do is they can put it in the run mode, and then they can pull the key out and take them with it. And that means some weirdo can't come in and plug into the PLC and change the programs because they don't have the key. So we'll look at the compact logic, and that's what it does. The 1100, anybody can switch it between the three modes. We just selecting it in a menu, and I'll show you how to do that. So we okay on the modes. So the programming applications has got two modes. It's got offline mode. This is when we create our program. We create our program offline. It's got the online mode where we can monitor the program, but also we can download it into the PLC if the PLC is in the program mode. So, well, right now I've got mine in the remote mode, which allows us to switch it with the PLC. Okay, got a couple more things, and once we get through with this, guys, we're going to cut out a little early. Program contacts that are controlled by the rungs outputs are simply called normally open and normally closed. The terms examine if open and examine if closed are rung contacts that are controlled by physical input devices such as a switch. So on my inputs, and this has caused a problem. So on my inputs, I use that symbol right there. This is examine if open. So what that means, it means it's true if the switch is open or input, but I will use the switch as and then this symbol right here is an examine if closed. So this is true if the switch is closed. So right now, when I come up here and look at my PLC in my program, so I think I got my PLC still running. So RS Logic 500. By the way, that's the little ladder diagram. So when you get your PLC, and no, you can't have a copy of this. License for this software costs a lot of money. I think they give RS Logic 500 away. They give it away free, I think, on the Rockwell website. You might check that out because it's such an old application, and they've already gone and starting to change over to RS Logic 5000 or Studio 5000. So one of my students said they got it for free. But when you get into what we've done, we've installed it on the computer, and then we put an icon on the taskbar. And this is going to be true for all your computers and on our laptops. So this is our program. And right here, this is an examine if open instruction. So what I've done when I look at my switches, and we're still in the monitor mode, I believe. No, we're not. Yeah, we are. So when I come up here, I'm going to bring up my camera. And here's that switch right here. So we got three positions. We got three things we can do with these switches. We can simulate. So right now in the center position, it's open. So when I put it like that, it's permanently closed. Or we got a momentary contact. So we can push it to this side, and it acts like a momentary contact push button, which we'll use that a lot. We'll use that feature a lot. So the problem is, I'm calling this a normally, if we call it normally closed, that means it's true when it's closed. But it's not closed, it's open. But when I come over here and I look at my program, it says it's true. Even though the switch is open, it says it's true. Because it's an examine if open, which means it's true if the switch is open. This is an examine if closed. So when I close the switch, the examine if open goes false, and the examine if closed goes true. Now what this does, it gives the programmer the ability to buy all normally open switches for sensors and everything for their line. And then they can tell it what to see, what's true and what's false by using examine if open or examine if closed. The only time this is illegal is when we use something called a stop button. So a stop button has to be normally closed. So when that guy drew that line diagram, he used a symbol for a normally closed push button. Well, now he's screwed, because if I use a normally closed push button, that means it's false. Another thing is a stop button has to be normally closed. So that means we need to use an examine if closed instruction. Why? Because what we want to do is if the wire breaks on the stop button, we want the equipment to stop. If you use an examine if open instruction and the wire breaks, you won't be able to stop it at all. So that's why anytime we have a stop button, we have to use an examine if closed instruction. But it looks wrong in motor controls. Because motor controls, we wire up a normally closed push button. This is not motor controls. This is a program. When we deal with input ports, and so this right here comes from this right here comes from an internal coil. So that's a normally closed contact. That's a normally open contact being controlled by this This is not true. This is not hardware. That's software. This right here is controlled by an input connected to an input port. That is an examine if closed instruction. So right now I have that switch closed. This is an examine if open instruction. Right now I have that switch. I have that switch closed. So up here it's false. Down here it's true. So that's very, very, very important, and we're going to push that and push that. It's different for input and output device, for actual physical input devices that are connected to an input port. You got to really, really, really pay attention on which instruction you're going to use. Normally, we'll use an examine if closed instruction for a normally closed push button, and this is examine if closed right here. But if you take in motor controls, that's going to freak you out. And that's one big problem we have, is people thinking that a normally closed push button is a normally closed contact. That's true, but in PLCs, on an input, that is not a normally closed contact. That's an instruction that says it's true if it's open. This says it's true if it's closed. So we'll talk about that a little more. So that's very, very important. So everybody's going to mess up on that. Somebody in this class is going to mess up on that. They're going to have a normally closed push button, and they're going to use that examine if open instruction, and their run's going to be false. And they're going to say, well, the push button's closed. But they're using the wrong instruction. Somebody in this class is going to do that. I don't know who's going to volunteer for it, but usually everybody does it, guys. So that's very important. That's a big difference in PLCs and motor and actual relay controls. You're not required to know this for IL 194, but we'll do this next class. RS links. This is where we install or we configure the driver for the communication port that we're using. We'll also look at the DHCP server, which allows us to assign IP addresses. We'll have to look at that and understand that a bit. But why? Because the DH485 is a very reliable, and it was supported by Allen Bradley PLCs for years. And then we got DeviceNet, we got Profibus. But what has happened over the years, Ethernet, this Ethernet port or this Ethernet communication standard, since it's been around and it's in everything, what happens is PLCs are moving toward Ethernet, but we don't call it TCP/IP. We call it Ethernet IP because it uses a different protocol to send the information. So that means you got to learn about IP addresses. You got to learn about static IPs. You got to know dynamic IPs. You got to know how to set up subnet masks. So that adds a lot to what we need to know. But like I said, we'll get into it in a lot of detail in PLC 2 if you take that class. we'll get into these communication protocols and more, and we'll get in depth of this Ethernet protocol, which all of y'all using it, but you have no idea about it. Some of y'all have heard IP addresses. Some of y'all hadn't. Some of y'all have heard about static IPs, and some of y'all hadn't. Some of y'all have heard about dynamic IPs, and some of y'all hadn't. And probably most of y'all, it sounds like I'm talking Latin to you. But if you're going to get into these communication protocols now on these PLCs, you're going to have to know a lot more than just hooking up a wire between the two PLCs to make them commute. And the more and more we get into this, the more we're connecting PLCs together so they can share data. So when you get in here, I'm going to show y'all the Amatrol line and show y'all it uses Profibus to communicate between the PLCs, and we'll look at we won't get into a lot of detail in this class. Like I said, if you want more detail on how to connect the PLCs together and how to set up the Ethernet and all that kind of stuff, then you'll just have to sign up for the second class. We just don't have enough time in here. So anybody got questions?